Hello, everybody. This is the Geralt Aquarius webinar for AGU 2020. We had some technical difficulties when we first recorded this webinar, which meant that the recording was not available at the end. So this is a re-recording of the original webinar. It may not match the original presentation exactly. However, we'll go through exactly the same slides and we will still refer to the questions at the end. My name is Will Rice. I'm the Global Sales Manager at Geralt. So today I'm going to be talking about the Aquarius Ocean Bottom Seismometer, its applications and its features that are new to the OBS world. So the whole philosophy around all systems at Geralt at the moment is all systems should be configurable, adaptable, and affordable. We're increasingly seeing the seismic community move towards very simple to use instruments that can be used in a number of environments. And we're often limited by funds available from government entities or from private organizations. Therefore, we need to make all instruments as easy to use as possible whilst being within financial constraints as well. So this presentation is going to take the form of 5 key areas. We're going to move through the sensor capabilities. These are the standard sensor capabilities that you would see on a data sheet. Then we'll move on to communication. After that, we'll move on to battery life. Now, battery life is fairly key with ocean bottom seismometers because we obviously don't have access to power quite a lot of the time. Then we'll move on to installation and recovery. So installation of the OBS itself, and then recovery once the deployment has been finished. At the very end, we'll talk about a few applications and possible future applications for the OBS. So to start with, sensor capabilities. Any of you who came to James Lindsay's presentation about the Certimus the other day will notice that the Aquarius bears a very similar resemblance to the Certimus. Now, this is because the Certimus is essentially inside the Aquarius. So the Certimus is a land sensor. It is operational at any angle. It's very portable. It's also very, very low power. So inside the Aquarius, we have the Certimus. The standard frequency bandwidth of the Aquarius is 120 seconds to 100 Hertz. A key feature of the Aquarius is that it is operational at any angle, plus or minus 90 degrees. We don't use a gimbaling action for this. I'll explain this a little bit later on, but this essentially means that we can land at any angle on the seafloor and the sensor will still work properly. This gives us a lot more confidence when we are in installations because we can drop it off the side of a boat and it doesn't matter which way it lands on the seafloor, it will still be able to function. As you'll see from the larger photos where we have the yellow syntactic foam, the Aquarius has an annular or ring shape to minimize the interference from seafloor currents. Seafloor currents do change direction. Therefore, if we have a rectangular or a square version of the Aquarius, we are likely to get different noise interference patterns depending on what direction the current is coming from. However, if we make it round, this means that whatever direction the current is coming from, the noise interference is likely to be very similar over time. Therefore, we can try to exclude it a lot more easily. Something I will come on to in the next section is the wireless acoustic seafloor to surface communication. This is a very key feature of the Aquarius in the sense that we can transmit seismic data from the seafloor to the surface without any use of cables. This means that during deployment, we can retrieve seismic data when we have been notified of an event using land stations without needing to retrieve the OBS. So the OBS can stay on the seafloor for more months, more years, and we can just pull off the data that we need at that instant. In addition to the seismic sensor, we do have standard auxiliary sensors. So these are hydrophones and an acoustic pressure gauge. Both of these have different variants. So for the hydrophone, we have 2 Hertz to 30 kilohertz, or a low frequency version from 0.01 Hertz to 8 kilohertz. In the same sense, we have the the absolute pressure gauge, which can have a resolution of 1 part per million or 1 part per billion. And this is all configurable at time of order. So as I said at the beginning, Grub is increasingly moving towards a situation where product standards are increasingly configurable by the user at time of order. These are not engineering or bespoke situations. These are simply choosing options like you would choose on your car. The standard Aquarius has a 6,000 meter depth rating. There are 2 pressure vessels actually, one which is rated to 4,000 meters, one which is rated to 6,000. The 4,000 meter version has more space for batteries. This means that we can deploy for longer, or it means we can transmit more seismic data in the same amount of time, because transmission of seismic data does take up a lot of power. And finally, the Aquarius is GPSA and USBL compatible. This means we can locate the instrument very, very accurately on the seafloor. So in the future, this could be used for GPS and geodetic studies, as well as seismic studies. So I mentioned that the Aquarius is operational at any angle. And if you look at the bottom of this slide, you'll see a very crude drawing of the Aquarius landing on some very bumpy terrain. It's landed on a number of different angles, and the Aquarius will function on each of these slopes. So small-scale seafloor bathymetry is very poorly constrained. We often have a good idea of what the rough bathymetry will be, but the exact square meter that we land on, we have no idea what kind of scenario this will be, whether there is a key rock in the way or a little bit of a wedge. If we land on that and it is outside of the usual tilt tolerances of standard OBS ranges, then we cannot proceed with the installation, or at least we won't know until the data is retrieved after we have recovered the instrument. The Aquarius uses digital feedback loops to compensate for these high tilt scenarios. So instead of moving the whole mechanism itself, we actually use the components and the electronics inside to keep all of the masses centralized within their frames, and we can adjust for all of this tilt. This increases the potential areas of research and the quality of data for all applications. So I mentioned previously that we have the traditional gimbal method for leveling OBS instruments. Now here you can see what the traditional gimbal method typically looks like. If you can imagine that the yellow shape in this scenario is, for example, the ballast. The green circle is a fixed glass sphere or a fixed dome. And inside we have the seismometer in blue with the components again in yellow. Now the seismometer is allowed to freely rotate depending on which way gravity is. And the red balls along the outside allow it to rotate inside the green sphere. As we vary the angle along the brown line, the seismometer is allowed to tilt. Usually these gimbals have a maximum tilt tolerance, and they also impart inherent noise into the instrument, which we cannot easily get rid of. Alongside the noise interference, gimbals also decouple the ground motion from the instrument. So when we want to faithfully record ground motion, we want to have the sensor as close to the seafloor as possible, sometimes even buried inside it. If we use a gimbal, then this inherently moves some of the motion away from the system. and therefore we don't have quite as good quality data. In addition to this, gimbals also present a single source of failure for the instrument. For example, if the gimbal fails, then it doesn't matter if your whole seismometer is working correctly. If the gimbal fails, then your whole sensor has failed. Therefore, it is a single source of failure for the whole instrument and something that cannot easily be rectified. So the Aquarius method is slightly different. As you can see in the previous slide, the Z and E components are always horizontal. Here, they are allowed to rotate and they remain fixed with relative to the actual frame of the instrument. So as I said previously, the Aquarius will use these digital feedback loops within the components themselves. Each individual component is not rotated to remain level, so we stay fixed with respect to the frame of the Aquarius itself. This allows for a high flexibility on unknown seafloor terrain because we can adjust this angle up to 90 degrees and we will still be able to function properly. Okay, so now moving on to communication. So this Aquarius is a free-fall portable OBS. This is in comparison to slightly more expensive and highly logistically challenging cabled OBS instruments. The idea with this instrument is that you can drop it off the side of a ship and then release some ballast a few months later and it will float to the surface again. However, this usually means that we have to wait several months to retrieve the instrument and retrieve any data associated with it. It also means that we have to wait several months to even know if our installation was a success or not. With the Aquarius, we have changed all of this. We have included an acoustic modem on the Aquarius itself, and then one for the surface, which can be mounted onto a boat or onto a wave glider or onto a permanent buoy or other infrastructure at the surface. These modems can communicate with each other. They can obtain state of health information. We can configure the instrument and we can receive limited seismic data to analyze noise performance during installation. During the deployment itself, we can actually record continuous data throughout the deployment on the Aquarius. And then whenever we have a time of interest, we can go to the Aquarius and extract that specific time of data onto a buoy up to the surface and transmit it back to land. We do not have to extract all of the data that is on the Aquarius itself. We can only extract the data that is necessary for us. So we do this in a very battery life efficient manner. Instead of recording individual files for each event, we simply record the timestamp that the event occurred. So for example, the event will cause a trigger, so that could be a threshold or an STA, LTA trigger. These timestamps are recorded in a table, and upon request or automated action, this event table is transmitted to the surface. Once an operator has this table, we can choose which timestamps we are going to request. And then data either side of these timestamps can be transmitted up to the top. This means we minimize the amount of data that is traveling through the water column at any one time, and also means that we lengthen the battery life and means that we can have the sensor on the seafloor for as long as possible. So we have two variants of the transducers or the modems here. These are omnidirectional or directional. So omnidirectional, as the name implies, has quite a wide arc and it sends acoustic energy in all directions. This is very useful for shallow waters, which means that you do not have to be directly above the instrument. And it's also very useful for communication at installation, but not during the deployment period itself. This is the least expensive version of the modem. And if you do not require communication during deployment and you only require satisfaction that your Aquarius has reached the bottom safely, then the omnidirectional transducer is the correct version. However, if we want to conserve battery life, or if we are going to deeper environments, we would perhaps consider the directional transducer. This is option B or option C in the diagram. So the directional transducer uses a much more narrow arc for transmitting data. This means it is far more energy efficient because we are not transmitting data to locations that aren't needed. It's very useful for deep water because by the time the arc reaches the surface, it has expanded quite a lot so that the boat does not have to be directly on top of the instrument. This is very useful for regular near real-time data retrieval to save our battery life. Okay, so event table and data extraction. We're just going to compare a little bit about the traditional methods on land versus what we have with the Aquarius. So on land, the traditional method is that we would trigger with a threshold either on STA, LTA, or an absolute threshold. And the event would be stored as a time window with a pre-configured pre and post event length. So for example, we would have a continuous recording stream and then individual files for each earthquake or each event that is recorded. With the Aquarius, we have tried to minimize as much of this as possible. So instead, we have stored all of these events as timestamps. Individual events are then extracted afterwards using a completely user configurable pre and post event length. So we only actually create these individual files when we actually want to. It's not an automated system. This requires much less battery and actually gives the user far more interactive nature with the instrument. So here is just a crude diagram showing the traditional method. We have a trigger time marked by the red line on the diagram at the top. The pre-event and post-event time windows that are usually pre-configured and fixed. So for example, here I've used 30 seconds pre-event and 90 seconds post-event. So each file length will be the same number of seconds, but depending on exactly what you have recorded, the file size may vary. With the Aquarius, we just store the event table. So we have the same number of records, but we only store the time that they occurred at. This means the only additional file in addition to the continuous record is the event table itself. The event table is very, very small, so we don't use up very much memory. And then when we do transmit it to the surface, we don't use very much battery life to do so. So here you can see in Discovery, so Discovery is Geralp's new software for operating the instrument family, which contains the Minimus, Certimus, Fortimus, and Aquarius. Here we can see the calendar view of events. So you can see in the middle that we have 54 events that have been recorded during this time. And each individual event is marked by a green line. Now you can see the operator here has clicked Get Data. And if I move to the next slide, we can see an example of what the operator would see. So if you see all of the files down towards the bottom, they are marked in mini seed files, marked by 0, 1, 2, 3, 4, 5, and onwards. We also have a time period or time window download file at the top, marked by the red ellipses. So we can either choose to download individual events if we have set some pre-configured times, or we can choose to download the table of events and just download the events we are interested in. Either way, this makes for a far more efficient battery life scenario. So here is a very simple diagram, just explaining everything I've just said. We have 3 stages. The Aquarius will send an event table to the surface. The event table is very small, doesn't contain any seismic data, and this will minimize the battery consumption. Secondly, the operator will manually or automatically select specific time events or time windows to retrieve. Any unnecessary data or events can be ignored, and only required data is sent to the surface, again, minimizing the battery consumption. All of this contributes to an operator-controlled or an automated system for extracting event-specific data, and this increases the efficiency and therefore the battery life. Carrying on with the battery life theme, as I said at the beginning, the pressure vessel inside the Aquarius can come in 2 sizes. That's rated to 4,000 meters and 6,000 meters. Inside each pressure vessel, there are 6 lithium-ion battery packs, and obviously these come in 2 different sizes depending on which size pressure vessel you've got. So you can see in this diagram the 6 packages around the outside. In each pressure vessel, these are available in short, medium, or long-term configuration. So, for example, we could take out 4 of these packs and only leave 2 of them in. That would give a short configuration. We could take out just 2 of the packs, and that would give a medium configuration, or we could leave all of the packs in, and that would give a long-term configuration. This allows us to configure according to costs or financial constraints, and any packs that are taken out will be replaced with dummy weights so that the buoyancy of the system remains constant. As with all of these things and standard land sensors as well, the maximum deployment time is dependent on the sensor configuration and however much communication you are doing with the instrument. For example, if you are only using the seismic sensor and you are not communicating any seismic data to the surface, then you will last for a very, very long time on the seafloor. If you are using all of the sensors at once, for example, the hydrophone and the APG, and you are transmitting data to the surface very, very regularly, then you will not last for so long on the seafloor. We can perform all of these calculations for you and tell you exactly how long we can expect the Aquarius to perform on the seafloor. But typically this is between 12 and 15 months, with a 21-month maximum if we're using the largest pressure vessel with the largest batteries and not communicating any data. Additionally, these batteries are equipped for super fast recharging, typically 1 hour per month of deployment. This means that during a recovery, we can recover an instrument, plug in the cable, retrieve the data. At the same time, we can simultaneously recharge the instrument. This means that we can go and recover another instrument while this one is being recharged. So then within about 12 hours, the first instrument we recovered should be available for redeployment. This means that we don't need to return to land, which means we minimize our ship time. Some more practical considerations to consider. We have now shipped 3 of these instruments by air freight, so we can confirm that all of the shipping and customs regulations and dangerous goods paperwork is all very easy to consider, and we have had no problems with this. So shipping via air freight is completely fine. Shipping via sea is also completely fine, as we've confirmed with other instruments. Okay, so moving on to some factors affecting the battery life. As I said, these instruments are affected by how much you are using and which sensors you are using as well. So if we look on the left-hand table, if you like, the standard configuration would be an Aquarius with the hydrophone working.